I would like to offer a few notes on probability distributions. First, let's look at some discrete cases. Imagine you toss a coin for 1,000 times or more, and perhaps in a perfect case you get 500 heads and 500 tails. And you can create a simple bar plot to show the frequency distribution of 500 for both heads and tails. Okay, such as what we show here with the figure. Okay, so the two bars here are of equal height. And this is a uniform distribution because every event here, head or tail, has an equal chance. Now, instead of talking about frequencies on counts, we can describe the distribution in terms of probabilities. So, in this case, head and tail have equal probability of 50% or 0.5 in the distribution shown here. So for the sake of discussion here, let's extend the binary case, head versus tail, to a larger number of exclusive outcomes. For example, imagine you roll a die for many times. And if you try sufficient times, all sides will eventually have the equal chance to appear. That is, each side from 1 to 6 has a probability of 1/6. Two very simple but important observations here. One, the probabilities of the 6 sides add up to 1 because they are exhaustive, mutually exclusive choices. And two, the probability distribution is a uniform distribution as they are all equal. It is a flat, horizontal line that characterizes the distribution. It's flat because everything is equal. So far, these are discrete distributions, but we can extend this to a continuous distribution. If the outcome is no longer limited to 1 or 2 or 6 or whatever, but rather it can be any number in the range of 1 and 6, we can still have a uniform distribution here with a flat line in the range of 1 and 6. And again, when we add all the probabilities together in the distribution, the total should still be 1. But because this is a continuous space, we're talking about infinite number of numbers, or infinite amount of numbers or values here. The outcome can be value 3 or a decimal number 3.1415678. So to add the infinite number of heights in the distribution is together essentially integration, or to calculate the area under the distribution line or curve. The result of the integration of the entire area here should still be 1. With a uniform distribution and a flat line, the area here, as you can see, is a rectangle, and it is easy to calculate the area. As you can see here, the area of the rectangle between 1 and 6 can be computed by the width, which is 5, times height, which is 0.2, and so the total area is 1. So this still meets the expectation of adding all the probabilities up to 1. However, we need to be very careful conceptually here. The height, 0.2 here, is not a probability value. It is what we refer to as probability density, but not probability exactly. Let's move further from the uniform distribution to a more common distribution in the real world, and we'll revisit this concept of probability density again. In the real world, you do not often see uniform distributions because it's really rare to see a situation in which everything is equal. A normal distribution or Gaussian distribution is much more common. For example, if we construct the distribution of adult male heights in the US, you will see the heights of adults are not equally likely. Instead, the majority of people have the average height around 70 inches, and much fewer are shorter than 62 or taller than 78. The whole distribution is a bell curve as shown in the figure here. This is again a probability density distribution. So if you integrate the curve of the total area, it will still be 1 or 100% of probability in total. When you pick a particular number on the x dimension, such as 70 inches in the middle, you will read the height of the curve on the y is about 0.1. Now, be very careful that this value 0.1 does not mean that there is 10% chance to have the exact height of 70 inches. Because there are really infinite number of values in the range, each exact height value has 0 probability. The reason is when we say 70 inches, we mean exactly 70.00000 with infinite number of decimal zeros. So it is impossible to get that kind of exact value. So what does 0.1 mean here? It means 0.1 probability density, or in another word, 0.1 probability per inch in the adult height. And this value will change if you change the unit of height. For example, if you switch from inch to centimeters, the distribution will remain the same shape, but the height will be different because the unit will change the density function. So what does the probability density entail? It allows you to compare probabilities at different values. For example, in the normal distribution here, you can still tell the probability of a height near 70 inches is greater than that in the proximity of 80. But to tell the exact probability, you need to offer a range. You can ask a question of the probability of an adult height between 70 and 71, and you can integrate the area in the range to find out. So back to the simpler example of a uniform distribution. The 0.2 value on y is not probability, but probability density or probability per unit. You can still tell that all the probabilities are equal by looking at that flat line. And you can ask a question about how likely you will get a value between 2 and 4 by multiplying the density, which is 0.2 in that range, and the range value, which is 2, and the result is 0.4. That's 40% of the chance you will get a value in the range of 2 and 4. Again, all probabilities will add up to 1, as you can tell by multiplying 0.2 times 5, which is the entire range.